Okay, the next three sections in Chapter 7 involving integration are pretty heavy. They're very important. They tend to give students some difficulties. So the next one is trig integrals. And I started and stopped this presentation. So something that I don't normally have is the first sort of slide ready. And before we get into all this, whatever. What is a trig integral? It's an umbrella term. It just means an integral whose integrand consists of trig functions. So, I mean, it's pretty self-explanatory. There's no, being an umbrella term, there's a lot of different ways or different types of problems that can come in. So there's no real recipes or like set formulas like we did with integration by parts. But we do have a few common structures. One of them is a trig integral that contains powers of sine and cosine. So I'll give you a second to jot this down. When I say powers, I mean sine squared, sine cubed, etc. And we typically do these through U substitution. In addition to the use of the following trig identities, what we call the fundamental identity of trigonometry, and then these replace sine squared and cosine squared in integrals. We'll get to that. I like to show these by example. I do want to add the book has, for this type of problem, the book has like a one-page explanation of a strategy, and you're welcome to read that. However, I kind of like to show by example and let the student kind of see the problem-solving logic involved. So let's jump into an example. Sine cosine example of a trig integral. Very common type of problem. I put these kind of things on many an exam. Let's have sine to the fifth cosine squared. So the reason U sub clearly would fit in here is because sine and cosines are essentially the derivatives of each other. So what do we want to make U? Well, we have two choices, two potential choices, not necessarily two right choices, but I could have a choice of U as sine, a choice of U as cosine, and if I do that, the du follows. Negative sign, right? Let's put the negative here. Okay, which one's right? One thing I want you to notice, and this is a key to doing this correctly, the du is a single power, right? It's a power of one. It's cosine or it's sine. There's no squares or anything like that. And that's basically non-negotiable. So if you start getting du's or thinking about du's or even u's with powers on them, it's no go. When you do these, you either have this or you have this, and that's it. Which one? Well, see, I go this way. Say I want to have du as my cosine. Well, let's see this. I'm going to bring this down here. Equals sine to the fifth. Now, what does my du need to look like? Cosine dx. So that's my potential du. All right. Well, if that's my du, this all has to be in sine. And there is no way to go from a single cosine to sine. If you go back to these identities, that's not going to happen. So this does not look like a wise choice. On the other hand, if we go this way, I want my du to be a sine. In fact, I'll stick the negative there. Sorry about that. That means I'll have sine to the 4, cosine squared. Now it's sine x dx, right? What I've done is broken the sine off of the 5, right? 1 over here. So this is now my du. And now this all has to be in cosine. This obviously is. And this can be made into cosine using this identity. Right? Sine to the fourth is sine squared squared. So let me do that. In fact, what I'll do is, let's do it like this. Let's work down. So this is out, okay? No go. This is in. And I'm going to replace the sine to the fourth with the cosine. Let me do it over here. I know I'm a little bit all over the place, but I have limited workspace right now. So it's sine squared squared. Sine squared is 1 minus cosine squared squared. That's sine to the fourth. There's the other two remaining cosines, and there's my du. Okay, so right, this is the appropriate u substitution. I'll do that right now. Yeah, I have to come down here. Letting cosine be u, I have 1 minus u squared squared u squared du. And you might say, well, look at this mess we have, and it's sort of a mess, but this is just really a polynomial in disguise. I FOIL this out and distribute the 2. This is just a polynomial. Okay, this would be, can I do this in my head? U squared minus, let's see, 2u to the 4. Cheating, I'm looking at this is out of the book. This is on page 519. Plus u to the 6. So I just expand this as a polynomial, and this is straightforward integration, and then the cosines go back in, and it's done. And that is how a lot of them go. I'm going to do another one. Cosine cubed. Another example here. Well, you look at this one and say, well, this isn't the same because I don't have the combination, right? But if I have a square, that can always be substituted out. If I have a cosine squared, that can always be substituted out, and I can make that happen, right? So this is my anticipated du. So I want this to be in sine, and that happens easily, right? So I have 1 minus sine squared cosine. That looks good. Now u is sine, du is cosine, and this substitutes out u squared du. And I mean, that's almost trivial for you at this point, right? So just to point out one thing, the reason those other identities are on that first sheet is, look at think of the last example, cosine cubed. What if you had to do just cosine squared? Example. Based on the other one, you know, I broke one off and then replaced what was there. And if I break one off here, I have 2 cosines. Well, you're never going to get one of them. You're never going to get one alone to a sine, right? If I were to follow suit from the last one and do this, and I think, well, this is my du, maybe, hopefully. Well, this is not changing. Okay, so that's not going to happen. So that's where the other identities come into play. This. And if I were to do the last one, if I substitute this in, this is an easy, relatively easy integration. So just in a nutshell, you get into a problem when there's no odd powers. Okay, this one had an odd power of 3. The last one, I'm going to put it back. All right, this had an odd power. The first one had an odd power, sine to the 5th. Because it's odd, that means you can break one off and have others remaining for replacement. Okay. So a lot of these go kind of the same way, and this is a common problem. Sine cosine trig integrals. Another common style, very similar, and I don't have a slide for this. We'll make it. Very similar idea. Not quite as clean though. So trig integrals, now we're going to have a different pair consisting of powers of tangent secant, and again it's kind of the same story, are often done by u sub, and these are called the Pythagorean identities, these squares. Okay, so notice this is one we don't have the analogous squares, identities for those. So we're going to use this. The reason this is a little bit, like I said, less clean, sine and cosine are essentially the derivatives of each other. I know one is off by a negative. That's not really the case here. It's a little murkier, but the same sort of principles apply. So again, let me find one. Okay, this is a tan to the 6 and secant to the 4. Let's use that. Okay, now again, I'm going to show you really your only two potential options. One is I can make tangent as the u, and the other one is I can make secant. Okay, and if I do that, my choice, the du's follow. Secant tangent, right? So again, this is how it has to be. It has to be this path or this path. So if I were to choose to go this path, my du has to be a secant squared. So I would have to break off 2 secants from 4. That's a 2. I'm sorry. I break 2 off. Making a mess. Okay, that's a 2. So this can be my du now. The question is, can I write everything else in tangent? And based on this previous identity, that's a yes. I can replace that secant squared with tan squared. I didn't need parentheses there necessarily. Tan squared x plus 1. So now everything's in tangent, and this will be my du. So again, I'm going to do this. So now if I'm going to make the choice, like we said, I need, let's see how this works. No, it's not going to work. Give me a second. Okay, I'll have to make a run tomorrow to get markers. This will have to do for now. So, again, this will be the appropriate choice. I'll substitute in. All I got to do now is distribute, and this is, again, you get polynomials out of these things. And then you back substitute, and your result has a lot of powers of trig functions. So this would be u to the 8th plus u to the 6th. And I mean, this is a slam dunk, right? Now, not everything fits into a category necessarily. There's, in theory, any combination of trig functions could be used. So just some other things that come up. And Now you might think automatically secant squared. Remember, that's the derivative. It's natural to think there's a very simple formula for this, but we haven't really seen it yet. We just saw that combinations of sine and cosine work very well, so sometimes we use some of our other identities, and we know that this is tangent. So what we have now is the ability to use this combination, and I use substitution. So again, we'll make that negative. Du over u. Okay, we recognize that as ln. So this will be negative ln. Don't forget the absolute value of u, which is cosine. And this is acceptable. I want to say usually what you would see, this is a -1 out front. Remember my logarithm property with these coefficients, they can be brought up as exponents. Usually we bring them out. But if this is cosine to the -1, that's 1 over cosine, right? That's secant. And I want to say that's probably what you would see in a table of integrals. So a couple other ones. Let's see a couple other ones. This one's a little bit obscure. I would never put this on an exam. Let's see. Secant. Cosecant is the same, really. Again, you might think, oh, there's a really basic formula for this. This is something that you would have to sit down and play with for a while. What I'm going to do is multiply by a specific form of 1. Anything over itself is 1. And this is not something you would just do naturally. Like I said, you'd have to play around with this problem quite a bit. What I'm going to do is distribute this. And I end up with secant tangent. Oh, forgot my argument. And this will be over, and I'm going to do this as well. I'm going to just flip-flop these so they match up better. Tan plus secant. Okay, you might say, well, why in the heck would you do that? Well, if I look at what I have here, I have a tangent plus a secant, and above I have their derivatives. So similar to what's above, if I were to let u be tangent plus secant, du is exactly what's above that. Secant tangent. Let me put this in parentheses. So what do you end up with? You end up with the same thing. Du over u. Ln of u, which is this, not a very pleasant antiderivative for secant. Cosecant is very similar. What else can we do? Let me look at the homework. So here's a good one. This, I typically put this on exams. Secant. So now I've thrown this extra x in here. And remember, I made this point before, when you do integration, you're going to have some trial and error, right? So you're going to try different things. Expect that, right? The more you do, sometimes you can see the end, but a lot of times you got to play around a little bit, especially at the beginning. What if I try this? U is x, excuse me. and dv as the rest. Well, that means I have secant du is then dx. So that integration by parts, v du, now I've made this simpler, and I just did this integral previously. So the previous one, like something like this, use something you want to have a formula written down for. I keep talking about this reference sheet, and I'm going to get one put together. So this would be, you don't want to recreate the wheel, ln secant. Okay, so you can, integration by parts can come into play. Like U substitution is pretty common, but anything really is possible. What if I mix and match? Another example. I want to mix and match. Let's try this. What about integral cotangent x cosine squared of x? Another thing I'll say, and this pertains to a lot of different problems, when you're dealing with multiple trig functions like you see here. Occasionally, not always, a good strategy is to get everything in sines and cosines. It's almost like they have a common language, you know? So if this is cosine cubed over sine x, let me see this thing. So yeah, let's do this. Let's make this a square and break one of these off. Okay, so you see where this is headed. This is now similar to the first problem I did. Okay, I'm going to replace him with the same identity. And now it looks like I have a good du if I make u is equal to sine, right? So let's do that. You got room here? Okay. Yeah, let me squeeze this in here. Cosine. And I get to this point. So that looks better. How to do that? I'm going to split up my numerator. So I'll have 1 over u. One over u minus u du. Interesting. I thought this would be easier. Cosine over sine squared, right? Cubed. Squared. Looks good. I thought this would have a much easier answer. This will be ln of u now. So that's ln of sine minus u squared over 2 plus c. Interesting. Okay. So point is, anything, I'll get new markers. Anything that we do can put in, right? But trig integrals is just an umbrella term for integrals with trig functions. So one thing that's clear, I think, is you want to know your trigonometry. You want to be comfortable with simple identities. There's 10 million identities in trig. We use many, but not that many, right? We use the basics. Like this, something like this, cotangent to cosine over sine, things like that. So know your trig identities, be comfortable with them, and practice some of these problems. This section isn't too bad, but I'm integrating it with an add-in, like an additional topic from chapter 10, because 7.3 is very heavy. And 7-4 is very heavy as well. It's some of the least popular among many students, but we'll get there, okay? Thank you.